This is crash course number 4, the fourth moment. This is moles and stoichiometry. And in this little mini unit or mini series, I'll be reviewing the kind of Regents questions you'll see regarding this topic. Okay, so in any case, this type of question is located early in the test, somewhere after or before bonding. Okay, so I'm trying to go in order how the test goes. So let's get started. Let's start with moles. Okay, now I'm not going to get into the detailed theory of moles because I've spent a lot of time on it, but you should know that a mole is a how many number. And we need so many times in this course, okay, a how many number is necessary. So when we're counting particles, when we need to know the number of the exact number of atom particles, and you say, well, why do we do that? Well, very simply, if I'm going to make hydrochloric acid in the most simplest case, a hydrogen atom and a chlorine atom come together to HCl. All right, so one of these and one of these, one of these. We just did some stoichiometry, which is using the ratio of how many. In a chemical formula of HCl, okay, there is one H, one Cl. Okay, notice we're counting the actual number of atoms compared to each other, and now we have a ratio of 1 to 1. So moles is very important for chemistry because it is essentially a way for us to go, okay, from measurements that we can do in the macroscopic scale, grams and liters, okay, and convert that into these ratios that we need as chemists or chemistry students. Okay, now where did it get started? Well, again, I have lectures below this that you can look at, okay, that talk about this, but essentially it all started with the gases. You know, we looked at gases and we took a equal volume of two different gases, and this is Avagodros' hypothesis. Let's say this was 10 liters of one gas and 10 liters of another gas, and this could be helium and this could be hydrogen. They came to the realization that when you have equal volumes of two different gases, as long as they're under the same conditions of temperature and pressure, and a lot of times they'll just say STP in this course, standard temperature and pressure, both gases are under the same temperature and pressure. Now what does that mean? Because helium is just an atom, a monoatomic gas, and hydrogen's a molecule of two H's. Well, we're going to treat each one of these as a single particle. That's what Avagodros stated. And if he said, if you're under the same temperature, then they have very similar kinetic energy, motion. And they're under the same pressure. That's the force pushing them down. So if you've got the same force pushing on them, okay, which we really know is other molecules hitting them, and they have similar motion, well, they have to take up, okay, a similar amount of space. Okay, now again, if you want to get into more details, I have bigger discussions below to talk about. But in any case, you should know same temperature and pressure, or the same conditions of temperature and pressure, because it's not always going to be at STP. These particles will occupy the same volume, and a lot of times you'll hear molecules. Okay, so same temperature and pressure, same number of molecules, but not atoms. Now, unfortunately, Amadeo Avogadro considered a single particle a molecule. The Regents considers a molecule two or more different atoms bonded. Okay, so a lot of times in multiple choice questions you'll see molecules, and I call this the same problem. Same volume, assuming same conditions, same number of molecules. Very important. So if I have 10 liters of helium, 10 liters of hydrogen, okay, they will, okay, have the same number of particles. Now they're not going to say particles, okay, they may say molecules, okay. What they will try to trick you or get you to say is these are the same number of atoms, and no way. Let's pretend in this box, and of course this is not true, that 4 helium atoms can fit. Well, what does that mean? That means at the current conditions of temperature and pressure, whatever that may be, 4 particles will stay in this box. If I was to increase the temperature, okay, if it was an opening, okay, this would leave. If I increase the pressure, I could force more molecules. All right, so let's pretend that only 4 particles can exist, in this container. All right. So in any case, I'm going to do this. There we go. And let's pretend that only 4 of these, and again, they're bonded to themselves, so there's 4 of these, I should say, particles as well, all right, are bonded to each other. Now, what's happening here? Well, we know that under the same temperature and pressure, conditions of temperature and pressure, this amount of particles can exist for each box. Notice they're the same. But the atoms are not the same. There are 4 atoms for helium, but there's, you guessed it, there's 4 particles, but each particle has 2 atoms, so there's 8 atoms here. Okay, and so therefore, of course, this does not have the same number of atoms. And it's rarely going to do that. For instance, if I have CO2, and I have water vapor, okay, gas, and I have, let's say, carbon monoxide, if I said, hey, which of the following molecules or which of the following compounds has the same number of molecules as 5 liters of helium, you would pick the other one that is 5 liters. Other choices could be 10 liters, other choices could be 15 liters. Obviously, same volume, same temperature and pressure, same number of molecules, but the atoms will not be the same, because if you look carefully, in one of these particles there is 3 atoms. In one of these there's only 1. So this actually has 3 times the amount of atoms in the same volume as this one. Okay? Now, the mole was a way for us to describe a quantity of how many. So we decided that 22.4 liters was going to be the container, the universal container at STP, because you have to keep temperature and pressure constant. So standard temperature and pressure was outlined in table A of your reference table. Okay, so we said that this was equal to 1 mole. So that means the amount of particles, okay, or helium in this case, that could fit in this container is equal to 1 mole. Which means if I have 22.4 liters of another gas, I have equal number of moles, which means I have equal number of particles. Okay? Usually molecules are what's used here. All right, so that's how that works. Now, if you have half a mole, 0.5 moles, then therefore you're going to have half of that, which is equal to 11.4 liters. Now, I'm sure all your good chemistry teachers have taught you to use a little bit of dimensional analysis. If I have 0.5 moles, okay, of an atom or a molecule of a gas at STP, I know that 1 mole of that gas is equal to 22.4 liters. And notice I put the moles in the bottom to get rid of that. And of course, 0.5 times that is 11.2 liters. And these are the types of conversions, liters to moles, you are definitely responsible for. A lot of times they're whole numbers. Okay, if I've got 2 moles, or if I have 44.8 liters of a gas at STP, and I want to know, hey, how many moles that is. Of course, you can probably do this math in your head, but if you get confused, or you get a number that's not nicely rounded like this one, please, or well, this one is, but if you don't get one that's rounded, then you would do this. Get rid of the liters. Liters go on the bottom, and 1 mole equals 22.4 liters, and you can see that I would get, okay, 44.8 times 1, divide by 22.4, that would give me 2 moles, okay? Now, of course, a mole represents a number. How many? Again, don't get lost. Okay, the idea is we're matching particles. 1 hydrogen atom to 1 chlorine atom made 1 hydrochloric acid molecule or hydrogen chloride molecule. Very important. Okay, so we have the same problem that you'll see. And then, of course, we'll have these conversions here. Now, the next point, once we decided that this was going to equal to 1 mole, and the reason behind this, for those that didn't have the theory in their class, the reason that it was decided that this was going to be equal to 1 mole is because this gave me whole number mass ratios. Let me explain on the next page here. Okay, let's say I have a container, 22.4 moles of my hydrogen gas. Okay, 22.4 liters. And let's say the same volume, 22.4 liters of helium. Okay, we know that they are different molecularly. These are two particles bonded together. It's a diatomic element, and this is just one. But we get that they're going to be the same number at this point. However, what we do is when we mass this box, we get a mass of approximately, okay, 1 gram. Now, actually, we would get 2 grams. There's two of them. But let's just pretend, yeah, we'll use that. So we actually get 2 grams, okay? And this one, we'd actually get 4 grams. Now you may say, wow, that's a 2-to-1 ratio. Well, actually, it's a 4-to-1 ratio. If you consider that hydrogen is diatomic, we're going to divide this mass in half to get actually a mole of atoms, right? There's twice the number of atoms in this box than this box. So I'm going to divide these 2 grams. We measure out 22.4 liters of hydrogen, of course, at STP. In this course, you're always at STP for these kinds of comparisons. You're going to get 1 gram. So this becomes 1 gram. Okay? This is already 1 atom, so it's 4 grams. Look what we're able to do. We're able to find out that if I have a mole of hydrogen atoms, okay, the mass is 1 gram. And a mole of helium atoms, hey, that's 4 grams. It's a 1-to-4 ratio. And if you look at the periodic table, they put those relative ratios, okay, as the relative atomic masses on the periodic table. And you notice the top number is the mass number on the periodic table. Where'd they come up with these numbers? It first came by comparing gases equal volumes. It's a nice rounded number, 1-to-4. Why they picked 22.4 liters? Because it gave me these mass numbers in whole ratios. And it gave me something more important. I'm able now to come up with something called a formula or molecular mass. For instance, let's go back to my original question. If I've got a box of chlorine and I've got a box of hydrogen, we now know by comparing them that this box is about, I don't know, 35 grams. Let's just round it off to 35 grams. So if I had a box, 22.4 liters of chlorine at STP, it'd be 35 grams. This is 1 gram. Now, if I want to put these together and chlorine plus H to make HCl, okay, we know that we would make 36 grams of that. And we already know that 1 mole of this plus 1 mole of that gives me 1 mole. Don't count the moles, because think with this. I have a chlorine atom and I have a hydrogen atom, much smaller, 35 times smaller or less massive. It combines to make, guess what? 1 particle. There it is, HCl. So how many particles do we have here? 1. How many do we have here? 1. How many particles? It's a bigger particle, it's bonded, but it's 1. So they would occupy the same volume. So it's a 1-to-1-to-1 ratio. So we would make, if I had a box of chlorine, 1 mole, and I had a 1 mole of hydrochloric acid, guess what? They would combine to make a box of HCl. Mr. Grotsky, you're doubling the amount of atoms. Yeah, but these guys are infinitely small. Remember Avogadros' hypothesis. Even though this is a particle here and this is a smaller particle, okay, they would combine to fill the same space. Okay, so 1 mole of HCl, and this is very important you understand, 1 mole of HCl is equal to the individual relative atomic masses, okay, that we get from the periodic table that came from these boxes. So my friends in chemistry, if I said to you, hey, what's the formula mass? Or I could also say, what is the molecular mass? Now in this case, they would say molecular mass. This is the mass per 1 mole of the object. For HCl, you would say, oh, okay, HCl, that means that 1 particle fits that box, and in 1 box of HCl, don't I have 1 mole of H? And what's the mass of 1 mole of H? Look on the periodic table, it's 1. What's the 1 mole of Cl? 35. So what is the mass of HCl? 36 grams for every mole, or for every box. Now, if I was to give you something like water, H2O, you would say, where do I start? Well, the best part is to see that, well, I have 2 H's per particle. In this case, we call it a molecule. I'm going to go to the periodic table, okay? And I go to my H, and there it is, 1.00794. I'm going to round that to 1 because I want the most abundant isotope. We've talked about that. So hydrogen is 1. And my chlorine is 35.4. We're going to round that to 35, the most abundant isotope. Okay, I'm sorry, in this case, oxygen, sorry, 15.994. So oxygen is going to round to 16, and of course my hydrogen is going to round to 1, and I'm off and running. So in my water, or box of water, mole of water, 22.4 liters of water, I'm going to actually have 2 moles of hydrogen, and that's a kind of a question here. In 1 mole of water, the question is, how many moles of hydrogen? Regents question. Well, in one of these, in 1 H2O, isn't there two H's? That's right. There's 2 moles of hydrogen per 1 mole of water. You understand that now. And if you have a box or some number of water molecules, let's pretend that water, again, fills a box up. Let's say the box holds 2. Let's say 2 of these represents a mole. Then don't I have, if I have 4 H's and 2 particles equals a mole, then I have 2 moles of H's. There's twice the number of H's per one of these. And that's how you do that. So when we're doing formula masses or molecular mass, what we're doing is we're just counting up how many of the individual atoms per mole and adding the total up. So for water, the molecular mass would be 2 H's, there's 2 moles of hydrogens, so 2 times, well, the mass of 1 mole of H is 1. It was 1.007, I think, we rounded that off, equals 2. There's what? 1 oxygen, so in one of these there's 1 oxygen, or in 1 mole of water vapor, or in this case just water, there's 1 oxygen, so 1 times the atomic mass of oxygen is 16. Okay, and if you notice, I add them all together, and this is 18 grams per mole. And you'll see that in many questions. What's the formula mass or molecular mass? Now, molecular mass is used for molecules, things that are covalently bonded. Formula mass is used for things that have formulas, and they're usually of ions in a crystal. For instance, I could have, let's pretend we have sodium phosphate. Now, sodium is +1. Phosphate is PO4, -3. So if I'm building that chemical formula, and a lot of times in this area, guys, they will give you names. So if I gave you sodium phosphate, okay, you'll look it up. Sodium is +1. Phosphate's -3. And if you don't know that, Table E will tell you. Okay, and we've been there a few times. Let's go there now. Okay, Table E, going to move in on my phosphate. There it is, PO4 -3. No reason not to know this. And my sodium, of course, I can look right at my reference table, and my periodic table will give me the charge, but you should be knowing this by now. There's my sodium, which is +1. Now I'm ready to make a chemical formula. Now you know where I got the charges from. Let's crisscross. You get Na3, 1 PO4. And if I said to you, what's the formula mass? They won't say molecular mass in this case, but this does not make a molecule. These are ionic compounds attracted to each other by differences of charges or ions. So I do the same thing. I have 3 sodiums. Okay, I have 1 phosphorus, 4 oxygens. Okay, so now I have to say, well, 3 times whatever the atomic mass, relative atomic mass of sodium is. So I have to go to my periodic table. And there it is, 22.98. We're going to round that to 23. Do not use the atomic number. Use the mass number. Okay, if you're not sure, it'll tell you right here. This is the mass per 1 mole. We picked that because it gave us the grams in 22.4 liters. Okay, so we have the 3 times 23. Okay, 3 is the rounded number. Then we have 1 times the atomic mass of phosphorus. Let's go find that. Phosphorus here, P, 30.97. We'll just round it to 31, most common isotope. Okay, there it is. 1 times 31, 3 times 23, and now we have 4 oxygens. Okay, so 4 oxygens, 4 times whatever the atomic mass of oxygen. But if we remember, we looked up oxygen already. It was 15.99. We rounded to 16. Okay, and now we're just going to now multiply these together. Okay, 3 times 23 is 69. 31 times 1 is 31, last time I checked. And then 16 times 4 is 64. Okay, and you add these together, and I get 164 grams per mole. And that is the formula mass, which is the same thing as the molecular mass. Note it's per mole. Okay, they use the word formula for ionic compounds and molecular for that, and that's a skill you have to have. And this leads us into percent by mass. The next kind of question you can see here is, what is the percent by mass of oxygen in sodium phosphate? Now, percent by mass, okay, means we're going to use a part over total. And we're going to make a percentage out of it, so we'll times it by 100. So in my question, what is the percent by mass of oxygen? Okay, so what I'll do, if I was starting from scratch, I would actually come up with the formula mass, 164, on the bottom. And the part that I was asking for in this question was oxygen, so that becomes 64. I found the mass of the part that I was asking for, and I times it by 100. And what I would get here is 39%. Now, in these types of questions, they could just give you the work and not look for the percentage. And you would see choices like, hey, 64 over 164 times 100, and that'd be the work. Okay, so we worked ourselves from mole concepts, a little bit of conversions, and now percent by mass. The next step is converting from moles to grams and grams to moles. Let's do that. Okay, and we'll use this same formula mass here for time considerations. Yeah, so let's say I wanted to convert, let's get rid of some of this. What if I wanted to now find, let's get that out. What if I wanted to now find, hey, if I had 0.33 moles of sodium phosphate, how many grams is that? So again, you start with your 0.33 moles, and all these types of math questions, conversions especially, start with what's given to you. And I'm going to use dimensional analysis. I'm going to get rid of moles, so 1 mole goes on the bottom. And how many grams equals 1 mole? Well, you would need a formula or molecular mass. We already have it, so that would be 164 grams. Now, some people teach divide and multiply and when to do that. I say use your units. Okay, if I have 0.33 moles, mathematically I want to cancel that out. I get grams. Somewhere on your test you're going to see grams to moles. Now, this is a very important conversion because it helps us go from grams that we can get from a scale and convert to a how many number. So this is an important conversion for chemists. We can't really count particles to match them, but we can sort of by converting them by using the formula mass here. Okay, so 0.33, or approximately a third of 164, and put that in your calculator, and you get 54.112. If they ask for the appropriate number of significant figures, when you multiply or divide, you round off to the least number of sig figs. Okay, this would be 2. So this would round off to 54, okay, grams. If I needed a third of a mole, okay, for whatever reason, I know all I have to do to get that certain number of these particles, I need 54 grams. Okay, and we can do it the other way. I can convert from grams to moles the other way. You know, if I had um, another example, let's say we had CO2, and I had, I don't know, 100 grams, 100 point grams of CO2. And I want to convert that into moles, into a how many number. How would I do that? Well, I'm going to get rid of grams. So grams go in the bottom. Nice and easy. No, I don't have to memorize when to multiply or divide. And 1 mole is how many grams? I need a converting factor. So now I have to do a formula mass. In one of these, there's 1 carbon. So 1 times the atomic mass of carbon, I have to go to the periodic table. And there it is, 12. Okay. And while I'm here, oxygen is rounded to 16. So I have 12 and 16, the relative atomic masses. I'm going to use their most abundant isotopes when I round. So the atomic mass is 12 for each of these. Since there's only 1 carbon for one of those, or in 1 mole of those, there's 1 mole of carbon atoms, right? 1 times 12 is 12. 2 oxygens. In 1 mole of CO2, there's 2 moles of oxygen atoms. So 2 times 16, 32. And what we get is that converting factor for every 1 mole, there's 44 grams. And that 44 would go up here. Okay, and lo and behold, okay, 100 divided by 44 gives me 2.27. 2.2727. Now, if they want a correct number of sig figs, notice that this has 3. Okay, because of that decimal point ending zeros count, so my number should be rounded to 3. 2.27. I need 3 significant figures. I'm going to stop here, but I'm going to look at, okay, this next number. Since it's less than 5, I keep 2.27 moles. And I know it's moles because the grams have canceled. Okay, very important skill you'll see, and then make you write that out. Now the next part is now we're going to use that skill to do something called building empirical mass. For instance, okay, let's pretend, that we had a compound that had hydrogen and fluorine in it. 95% of the mass of the entire compound comes from fluorine. Okay, 5% of the entire mass comes from hydrogen. Okay, this is a percent by mass. Okay, this is exactly what we just did. We have these values of percent by mass. Now what we want to do is build an empirical formula, lowest ratio formula. We know that formulas are not built on mass. We're not going to say H, okay, and 5 and F 95. These numbers in chemical formulas are not percentages and they're not masses. What they are is a ratio of how many. I've got to convert this percent by mass into the actual number of F atoms. That's what these numbers equal. And if you haven't guessed it, we have to somehow get to moles. So how do we do this? We're going to assume something. We're going to assume that we have a working video here. We're going to assume that we have a 100-gram sample. When I do that, this immediately gives me 95 grams of fluorine. Why? Because 95% of 100 is 95. This gives me 5%. So 5 out of 100, 5 grams of fluorine. Now, again, I still can't do this. I can't put H95 and H5, I should say. I can't do H5 and F95. It's not a difference in mass. Okay, it's how many. So we have to convert to a how many number. We need moles. Divide by grams, because grams will cancel. And I know fluorine from the periodic table, atomic mass is 19. Okay, I'm assuming I know how to look for that now. And I did this wrong because I put the 19 where the grams weren't. Right? So I'm going to put the 19 here. 19 grams equals 1 mole. It's a nice way to check. And hydrogen, as we've done previously, is 1 gram for every mole. I'm just converting to moles here. Okay, what do I get? Well, we put this in our calculator. 95 divided by 19. That gives me a nice round number of 5. And 5 divided by 1, if you don't believe me, put in your calculator, is going to be 5. We have 5 moles of fluorine. and 5 moles of hydrogen. Okay, next step, we're going to make a ratio. How do we do that? We divide by the smallest number. In this case, they're both the smallest number, so 5 divided by 5, 5 divided by 5, we get 1 apiece. And guess what? This is a how many number. This is a how many number. They are the same. We have equal numbers of H's and F's. How can that be if 95% of the mass is fluorine? Easy. Okay? Fluorine is more massive. So this is HF. Okay? And that's its empirical form. There's 1H to 1F. Now, there's one more type of question, and that could be something I call the box question. In this question, they're going to give you the empirical mass already, and they're going to give you the molecular mass to be 180 grams per mole. And they say, hey, what is the actual molecular formula? Okay, well, here's what I do. I draw myself a nice box. And I know the molecular formula is always a whole number ratio. So I write the molecular formula here. This is the empirical formula. The empirical formula is the lowest ratio, so I put it on the denominator side. This side is the chemical formula. This is the mass side. So what they gave me was the empirical formula to be CH2O. They gave me the molecular mass to be 180. They're trying to figure out what the actual formula that exists in nature. So that what I do here is I find the mass of this empirical. I have 1 carbon, which is 12, right? 1 times 12 is 12. I have 2 H's. Each H has a mass of 1. That's 2. It's right off the periodic table. And I have 1 oxygen. 1 times 16. These are all from the atomic mass periodic table. Gives me 16. I add these together. Okay, it's my 10. 6 and 4 is 10. And I get 30. So my empirical formula mass is 30 grams per mole. The actual whole number ratio of that, okay, is actually 180, the molecular mass, or the molecular formula. This is the formula side I should have put. All right, well, 180 divided by 30, okay, is 6, which means for me to go up, we times everything by 6. So if that's true, again, 180 divided by 30 was equal to 6. So if I times everything by 6 to get 180, I times everything by 6 here. 6 times 1 carbon is C6. 6 times 2 is 12. And then 6 times O is O6. And my answer, party people, okay, is C6H12O6. All right. Okay, the next type of problem is stoichiometry. You only really have mole-to-mole problems here. Okay, I'm going to show you both ways. That might be helpful. Here's the problem. Consider if I have 8 moles of oxygen, how many moles of water would I produce? So look at your mole ratios. First of all, your reaction has to be balanced. Okay, and I should balance it for you. Law of conservation of mass states that we should make sure we have the same number of atoms. Now, here's my formula. 2 H's on this side, 2 H's on this side. 2 oxygens, 1 oxygen. So I balance by putting a 2 in front. And of course, I'm going to put a, well, this gives me what? By having a 2 here, this gives me 2 oxygens, 4 H's. And to get 4 H's on this side, I put a 2 here. And of course, there's nothing in front. And that's how we balance. And of course, again, if you need to, 4 H's on this side, 2 times 2 is 4, and then 2 oxygens. We have 2 oxygens, and over here we have 2 times 2, 4 H's, and 2 O's. That's one quick way to make sure that you have the same number of atoms on both sides. It's called law of conservation of mass. Notice the charge is 0 on this side and 0 on this side. Don't have any individual ions here. So charge and mass are conserved, as well as energy if you had that mixed in. So back to our stoich problem though. I gave you 8 moles of O2. Here's how I would teach it. Given 8 moles of O2, and I want to get what? moles of water. I'm going to use something called the mole ratios from these stoichiometric coefficients. And before I forget, nothing in front implies 1, coefficient of 1. So if they ever ask for the sum total of all the coefficients, 2 plus 1 is 3, 3 plus 2 is 5. Any case, getting rid of moles. For every 1 mole of O2, now in our other conversions we were using getting rid of moles. We're not really getting rid of moles here, so I shouldn't put that here. I want to get rid of O2. So all the other conversions we've done in this little crash course, okay, we got rid of the individual unit. Here we're just going to get rid of the chemical. So I'm going to put O2 on the bottom. And I know that there's 1 of these per 2, and that's where I'm getting it from, waters. Okay? 8 times 2, you're going to see divided by 1 is 16 moles of H2O. It's as simple as that. Now there's another way to do it. I hesitate by showing you, but people like to learn from this. If I have 8 moles of O2, and let's put this right in there. So if I have 8 moles of O2, put the 8 here. How many moles of water? X, coefficient becomes the denominator, X over 2, right? This is an arrow. This is 8 over 1, right? That's where I got that from, over X over 2. Again, the coefficient becomes the denominator. Solve for X, you'll get 16, okay? Same way. All right, and that's as far as it goes with stoichiometry on the Regents, moles to moles. Now, let's do one more balancing, and we'll almost call it a day. Let's do, I don't know, sodium carbonate like we had before. We'll do sodium carbonate. And we'll do, let's not do sodium carbonate. I don't want to, sodium phosphate, sorry. Sodium phosphate, like that we had before, plus, let's do ammonium carbonate. And we need 2 of these ammoniums, right? Because each ammonium is plus 1. And now we're going to do a reaction, and you should be able to predict, okay, what's going to happen here. This is a double replacement reaction. The positive ions are in front. So we know sodium's plus 1. This is negative 3. Ammonium is plus 1 in table E. Carbonate's negative 2 in table E. These are polyatomic ions. Now we're going to basically switch partners. This positive sodium hooks up with this carbonate. So I'll make sodium carbonate. Now carbonate is negative 2. Sodium is plus 1. If you're going to crisscross, make sure you reduce to lowest terms. But in any case, you need 2 sodiums per 1 carbonate. Once you've used your ions to build your chemical formula, that's neutral. Okay, that's why there's no charges left over. Then we know that we've built it correctly. And then the next one, we have ammonium phosphate. Right, just switching partners. Ammonium is plus 1. Phosphate is PO4 negative 3. So we're going to need 3 of these. This has to go in parentheses to show we need 3 of everything inside. And lo and behold, right there is what we have. Our correct chemical formulas, we predicted it. And now let's balance this. Okay? Now when you balance reactions that have polyatomic ions, I find it easy to keep the polyatomic ions together. All right, let me show you. I have 3 sodiums. I have 2 sodiums. Problem already. Okay, so 2 and 3, I need a common factor, and 6 is a common factor. Both numbers go into that nicely. So I'm going to put a 3 here. 3 times 2 is 6. I'm going to put a 2 here. So my sodiums are balanced. Now notice something. I have 2 sodiums, but remember this distributes. I have 2 phosphates, keeping the phosphates together. I have 1 phosphate. So I'm going to throw a 2 here. 2 phosphates. Okay, now look at this. That gives me 2 times 3, 6 ammonium ions, keeping this together. 6, well I have 2 here. I would need a 3 in front to give me 3 times 2, 6 ammoniums. And look at this, 3 carbonate ions, which I already have because I balanced my sodiums. So I kept these clusters together, okay, and I treated them as elements. So 2, 3, 3, 2. If they wanted the sum total of the coefficients, that'd be 5 plus 3, 8. 8 plus 2 would be 10. So these are the basics of stoichiometry you'll see, okay, in this course. There's one little smaller component in redox, okay, where if I had something like copper plus 2 ions, and I know that I need 2 electrons, 2 negatives, to make these coppers 0. Notice both sides have this charge of 0, okay, charge is conserved. And if I said, hey, if I had 4 moles, okay, if I had 4 moles, let's say, of copper plus 2, the question is, how many electrons, moles of electrons? Well, look at the ratio. For every one of these, there's 2. Okay, so if I put 4 moles of copper plus 2, I want to get rid of copper plus 2 on the bottom, and I know that there's 2 electrons. Notice it looks very similar. 4 times 2 is 8 moles of electrons. So in redox, you'll have very similar types of things, but you'll be using the how many number of moles for the element and its electrons based on what it needs to become as its product. Okay? Hope you enjoyed that.